All right, class, welcome. Today we're going to be covering 2.4, and this is going to be linear inequalities. Your handout says linear inequalities and problem solving, but we are not going to do the problem solving part. Okay, so first couple of things we want to talk about, like what is an inequality? Well, an inequality is an equation, basically, that can be written in this format. Now this looks exactly the same as the linear equations that we were talking about. The only difference here is this sign right here, this less than sign, okay, which could be also written less than, greater than, so it could be written like this or like this. So this means greater than, less than, greater than or equal to, less than or equal to. Now, if it's written like this, when you're writing your graph or your interval notation, it will have a parenthesis. If it's written with an equal to sign, it will have a bracket. The parenthesis means that the value itself, and we'll talk more about this, the value itself is not included. Okay, the value itself is not included, and the bracket means to include the value. Okay, so when there's no equal to, we don't include the value. When there is, we do. Okay, so how is an inequality different? Well, if I were to go and say, I have 3x and that's equal to -9, then I would divide this by 3 and we get that x is equal to a -3. And remember that this is an equation, so we get one unique solution. Because this equation is conditional. Remember we talked about the different types of equations, so this is a conditional equation. Okay, because this equation is conditional, then it does have one unique solution. And if we were to draw this unique solution on a number line, we would say that is this dot right here. Okay, so how is an inequality different then from an equation? Well, an inequality isn't just this one specific spot. If I had this same inequality here, but I had a greater than -9 and I divide by 3, then I would get that x is any value greater than -3. Okay, so this has limits on the solutions, so there's not one unique solution. There are multiple things that would make this true. So for instance, if I had 0, 1, 2, 3, and I plugged in the value -3 itself. Okay, so -3 is greater than -3. It's not greater than, it's equal to, so this is false. So because we have this not equal to part of the statement, this is false. So we're not going to include this value here. But I could plug in a value larger than it and get -2 is greater than -3. That's true. Okay, so the value on this side of this line, if we were to draw a line here at -3, this is true. But if I were to put a value over here in, let's say -4 is greater than -3, this is false. Okay, so this is false. So that means that all of the values on this side of the line would make this statement true. So there's not just a single dot or point in time. It's not a linear equation with a unique solution, one unique solution. It's an inequality, which means there are multiple values that could make this statement true. As we continue to go on forever in this direction, we're approaching a positive infinity. Okay, so this is the solution right here, the way this is written for the inequality. Okay, this is the graph. And if I wanted to write this solution in interval notation looks like this. I would literally just take this parenthesis here and say -3, and then this is approaching a positive infinity. So this literally means go all the values from -3, but not including it. Remember, this means not including it. Okay, not included. To positive infinity, and anything in that range will make this inequality true. Okay, so this is called interval notation. The other way to write this is called set builder notation. Set builder notation looks like this. It's got that little ugly squiggly thing I can never write, and then it says x is such, so x is such that x is all numbers greater than -3. End of squiggly. Okay, so these all say the same thing. So this is my original inequality written in this format. I solved it. You can notice here that the solution looks very much the same as the set builder notation. It just has this different x is such that x is all the values greater than -3. I have my test points that I tried here, one on this side and one on this side. This side was false and this side was true, so we know we're talking about all of these values, and this is approaching a positive infinity. Again, this is how you write it in interval notation. Okay, so the way that an inequality differs from an equation is it's got multiple solutions, not just one unique solution. Now again, of course, we had those other kinds of equations. One was contradiction. We're not talking about contradictions. We are also not talking about identities here. So when we're talking about the difference, I'm only comparing these to conditional equations, assuming that the original statement is a true statement. So one more thing that I wanted to point out here that we went through is that infinities always have has parentheses. Okay, where we're talking about positive infinity or negative infinity, it's going to have a parenthesis because you can't include the value of infinity because it's not finite. Okay, it's infinite. Okay, so we've got what an inequality is. This is how it's written. These are some notes about inequalities, the difference between an inequality and an equation. We just talked about set notation versus interval notation, okay, versus just the plain solution. So let's do a couple more of these, but before we do that, I want to talk about some things you should know. If I start with this statement, 5 is greater than -2, and this is a true statement. Okay, and then I say times this side by 10, and times, so we're going to times by 10, times by 10. Then I get that 50 is greater than -20. This is still a true statement. So this is a property that says I can multiply both sides of the inequality by the same thing, and as long as I do, it'll remain true. If it's positive, okay, what happens though here, if I start again with this 5 is greater than -2, and I times it by a -10, okay, then we get that -50 is greater than 20. -50 is not greater than 20, it's all the way over here, and 20 is here. So this now is a false statement. So what happened here is when you multiply or divide by a negative, you have to flip the sign. Okay, so that is another note to remember. If you multiply or divide by a negative, you have to flip the sign. And this is why, because it's no longer true. Okay, so I can multiply and divide by positives, but not by negatives. If I do negatives, then I have to flip the sign. You must flip the sign. The reason why is it keeps the integrity of the statement true. So back to that, if I have -50, I said it was greater than 20 when I was multiplying it. If I flip the sign, now it's a true statement. So in order to keep the integrity of the statement, we have to flip that sign. Now I can add and subtract stuff all day long. If I start with this true statement of 10 is greater than 2, and I add 2 to both sides, 12 is greater than 4, this is true, this is true. If I subtract 6 from both sides, 6 is greater than -2, this is still true. So it doesn't matter if I add or subtract. I can add and subtract all day, the statement stays true. But the second that I go and multiply or divide by a negative, so now I'm going to divide by a -2, then I'm going to get negative 3 is greater than 1. This is a false statement. So again, to keep the integrity of that statement, I have to flip my sign. Now this isn't intuitive or easy to see when you're working with a variable, so that's why I showed you with constants here how this is true. Okay, so we're going to go through now and do a few more problems, keeping in mind these few rules that I wrote over here and the reasoning for that. Okay, so I'm going to kind of leave this over here, and let's say if I gave you the set notation that said x is such that x is less than 2, and said to graph this. So the instructions here would be graph. Well, I'd literally go to my number line. I have the number 2. This tells me that the number 2 itself is not included. And I'm looking for anything that would make this statement true. If I plug in negative 1 is less than 2. This is true. So I'm looking at all of the values then. So we plugged in negative 1 over here. So if we have this dividing line at 2, okay, because that's what we're comparing to, we're talking about everything this direction. This to the left is all of the stuff that's going to make this true. So this is approaching a negative infinity. Okay, so if I were graphing, I would say I have my arrow pointing this way and I have everything but 2. Okay, to translate this to interval notation, I literally read the graph from left to right and say I've got negative infinity, 2, positive 2, not including positive 2 because there's no equal to sign here. Okay, so this is taking set builder notation, or a solution basically, and putting it on a graph. Okay, let's do a couple more of these with fractions and decimals. Okay, graphing x is such that x is greater than or equal to a negative 4.5. Okay, so I'm going to get my number line out here. I've got negative 4.5 is the point I'm looking at. Okay, that looks like 45. Negative 4.5. All right, well, I'm going to plug in 0. 0 is greater than or equal to negative 4.5. 0 is greater than or equal to negative 4.5. This is a true statement. So I am talking about all of the values on this side of my imaginary line here. This is approaching a positive infinity. Okay, but because I have this equal to part of the statement, because this is greater than or equal to, then the value of negative 4.5 itself is included. So if I said, is negative 4.5 greater than or equal to negative 4.5? Why, yes it is. It's the equal to part of the statement that makes that true. So this value is included. Okay, and again, we're approaching positive infinity. If I were to take this and put it in interval notation, I would say start at negative 4.5, again reading the graph from left to right, include negative 4.5 and go all the way to infinity, but do not include it. Okay, we're going to do a few more problems here. A little bit of a compound inequality where there are more. X is such that negative 3 is less than or equal to x, and it's less than 4. So it fits both of these parameters. So what does this mean? Well, this just means that on my number line, I've got 2 points that matter, my 2 critical points. Okay, so we've got 0 here and 4 here. So my dividing lines here is this line here and this line here. So what I want to know is this stuff over here make that statement true? Does this stuff in between here make that statement true? And does this stuff on the right make this stuff true? Well, if I plug in a negative 4, negative 3 is less than or equal to negative 4, which is less than 4. this part of the statement is true, but this part of the statement is false. If either part of the statement is false, then the whole thing is false. So over here, -4 is not a value that will work. This is false. Okay, if I plug in 0, -3 is less than or equal to 0, which is less than 4. So -3 is less than or equal to 0. That's true. And 0 is less than 4. That is also true. So this is all true right here. So between here and here, I know is true. Over here is false. Let's plug in 5. Whoops. -3 is less than or equal to 5, which is less than 4. So this part of the statement is true, but this part of the statement is false. So because part of it is false, then the whole statement is false, because this is a single statement. Okay, so we are talking about the values between -3 and 4. But what about the value -3 itself? Well, because it's less than or equal to it, then -3 is equal to or satisfies the equal to part of that statement. Okay, and then this less than, again, there's no equal to, so it's going to have a parenthesis. All right, so this is our, again, our set builder notation, or our solutions here. And we are going to say, if I were to translate this into interval notation, I would say I'm talking about all the values including -3, 2, 4, but don't include 4. Okay, so that would be my interval notation for that problem. Let's do one more of these compound inequalities here. And then we'll get to just a few problems that we're actually going to solve. This one says that x is such that 3 is greater than or equal to x, which is greater than -4/3. And again, our original assumption is this statement is true. This inequality is a true statement. Okay, so x is such that this is the case. Again, all I'm going to do here is put those critical points on my number line. So 1, 2, 3/3, 4/3 would be right here. So this is a -4/3. And we're dividing this number line then into these sections, and we're trying to figure out what makes the statement true. Okay, so 3 is greater than x. I'm going to plug in the value of 0 in the middle here. If x were 0, is this statement true? 3 is greater than or equal to 0. That's true. 0 is greater than -4/3. This is also true. Okay, so I know that this in here, the values between here and here, are true. What about the value -2? Three is greater than -2, but -2 is not greater than 4/3. So this part right here is false. So this side is going to be false as well. Okay, and the same thing would be true if we plug in 4 on this side over here. 3 is not greater than 4, so this is false. This part of this statement is false. Okay, so question here is, do we include the value of -4/3? Well, since x is only greater than it, then the value of 4/3 itself is not included, but the value of 3 is. Okay, so we are going to erase that. We're going to read this graph from left to right and say I'm talking about all the values from -4/3 but not including it. Remember, that's what this means. Until I get to 3, including 3. Okay, so this is my graph, this is my interval notation, and let's solve some inequalities. The steps for solving the inequalities are the same as solving linear equations. We're going to do steps here. I'll write them abbreviated. Remember, our first step is to simplify on each side. Our second step is to isolate the variable. Remember, I'm going to move stuff around through addition or subtraction at this stage, away from the variable. My third step is to get the coefficient to be 1. And the way we're going to do that is we're going to use multiplication or division, remembering that if we multiply or divide by a negative, we've got to flip our sign. Okay, and then the last thing is, if I was dealing with fractions, I would want to simplify or reduce those fractions. And if I'm dealing with fractions up front, when I simplify on each side, I want to use the LCD to remove fractions. Okay, so let's go through then a few of these, and again, remember our steps are going to be the same as solving an equation, a linear equation in one variable. Whoops, let's do these two first. Let's do x plus 3 is less than 1, and a negative 2.3x is less than 6.9. Okay, so to solve these, they're not solved for yet. I'm going to have to undo any addition and subtraction. So I'm going to subtract 3 from both sides. I'm subtracting 3, so I do not need to flip the sign. I can add and subtract all day long. As long as I do the same thing to both sides, then the inequality will remain true, or remain intact. Okay, so this right here again is my solution. So I just solved this. The solution is that x is less than negative 2. The graph, however, is different. The graph is the visual portion, how we visually represent that. We've got 0, negative 2, and I'm talking about all the values. X is everything that is less than negative 2. Okay, this is approaching a negative infinity, and it does not include negative 2 because I only have this portion here. So that is going to give me a parenthesis. Then if I want to write this in interval notation, okay, then I'm going to read this graph from left to right and say I'm talking about all the values from negative infinity always has parentheses, to negative 2, but not including negative 2 because there's no equal to part of this statement. Okay, so this is solving. For this one, we're going to use the multiplicative property, or we are going to get the coefficient to be 1. The quickest way to do that is to divide both sides by a negative 2.3. Remember though that when you divide by a negative, you have to flip this sign. And this would give me then a negative 3. When I divide 6.9 by a negative 2.3, I get a negative 3. And I have to flip the sign, so I'm going to, again, here's my solution. And I'm going to draw this on the number line. We're talking about negative 3. And x is everything that's bigger or greater than negative 3. So it's all the values to the right. This is approaching a positive infinity. And the value of negative 3 itself is not included. Okay. Again, because I divided by this negative, I had to flip that sign. So I'm going to read this and write this in interval notation. I'm going to say I'm starting at negative 3 and all the values from negative 3, but not including it, to a positive infinity is the solution to this inequality. I've got 4 more problems I'd like to go through here, so just hang tight. And we're gonna get the solution, graph them, and write them in interval notation. If you need to pause the video or rewatch part of it, you're more than welcome to. Let's do 3x plus 4 is greater than or equal to 2x minus 6. Now, a strategy here is I want to isolate my variable. There's nothing I can simplify. These can't be combined, so I'm going to move my variable over here. And because I did that, let's see, we've got x plus 4 is greater than or equal to a negative 6. I want to get rid of this 4 because it's connected to the variable, so I'm going to subtract 4 from both sides. As long as I do the same thing to both sides, then we're good to go. So the solution here is that x is greater than or equal to a negative 10. Now again, I can add and subtract all day long and not flip this sign. Doesn't matter if it's positive or negative. So my solution is x is greater than or equal to negative 10. The graph, I'm going to have 0 and all the way over here a negative 10. X is everything that's greater than or equal to that. So we're talking about all the values that are greater than. Again, over here is approaching positive infinity. And because I have this equal to part of the statement here, then we are going to have a bracket. So this is the graph here. Reading this for interval notation, we'll say I'm going to start at the value negative 10 and I'm going to include it. So negative 10 would make the statement true. And I'm going to go all the way to infinity. And of course we always have a parenthesis there for infinity. All right. Next one we should do is has a little bit of cleaning up to do in the up front. All right, so again, my first step here is to simplify on each side. So I'm going to perform every operation I can over here. Can't combine those, so I'm going to multiply. I'm going to get negative x plus 3 plus 2, which is going to give me a negative x plus 5 on this side. That's as simple as this side gets. Over here, I'm going to distribute as well. So I'm going to get a 6x minus 15 plus x. This sign isn't, I'm not doing anything with this sign, I'm just simplifying on each side. When I combine 6x and x on this side, I'm going to get 7x minus 15. Now from here, I'm going to move my variables to get them on the same side. So I'm going to subtract the 7x. You could add x, it doesn't matter. I'm going to subtract the 7x, and the reason why I like to move my variable to the left when I'm working with inequalities, because the arrow points the same way. So if you have your variable on your left and it says greater than something, then the arrow on the graph will point this same way. Okay, and if the variable's on the left and it says less than something, then the arrow on the graph will point the same way as the arrow in the inequality. Just a little tip there. Okay, so I have a negative 8x plus 5 is less than or equal to a negative 15. I'm going to subtract 5, and we will get then that negative 8x is less than or equal to a negative 20. When I divide by negative 8, this is where I am. So I've isolated my variable here. There's nothing connected to it except for through addition of subtraction. So now I need to get the coefficient to be 1. But remember, I just multiplied or divided by a negative right here. So because I did that, I've got to flip my sign. Okay, and I need to reduce this fraction. I can take a 4 out of both. If I divide both of these by 4, then I get a 5/2, and the two negatives will make a positive. So now this is my solution here. Okay, so x is anything that is greater than or equal to 5/2. Well, what does that graph look like? 5/2 is the same thing as 2 1/2, by the way. So we've got 0, 1, 2, 3, and 2 1/2 is right here. We'll write it as 5/2. And remember how I said this is super cool. When I have my x on my left, if my arrow's pointing this way, again, x is all the values greater than or equal to this. So it's always going to be pointing this way if my variable is on my left. So it's going to be approaching infinity. And because I have this equal to part of the statement, it will include the 5/2. Okay, so writing this in interval notation is going to be going from all the values from 5/2, including it, to a positive infinity. So here's my graph, and here is my interval notation. This one had a lot of cleaning up to do up front, the simplifying on each side, watching signs. Okay, the last two I want to work on are fractions here, and then we will wrap this section up. right, so if we have 3/4, it's going to be multiplied by x plus 2, and that's going to be greater than or equal to x minus 6. Well, nobody likes that this 3/4 is here, so we want to get rid of it. But remember, this is the same thing as if I had 3 times x plus 2 all over 4, and that's greater than this x minus 6 all over 1. So you can think of it as written this way. So what I want to do is I want to get rid of this 4. That means I'm going to multiply both sides by 4. Or I'm going to build this fraction up, so I'm going to multiply this by 4. Because I'm multiplying both the top and the bottom on one side by 4/4, it's the same thing as multiplying this side of the equation by 1, which isn't changing it. This one already has a 4, so we don't need it. Remember that this 4, though, belongs to both of these. When I multiply this 1 by this 4, the bottoms will both be 4, and I can just get rid of the bottom. Okay, so what's left here on top is this 3x plus 6, and over here we're going to get a 4x minus 24. Okay, again, I'm going to move my variable to the left just to make sure that I can read the inequality easily. That's going to give me an negative x plus 6 is greater than or equal to a negative 24. Subtract the 6 to isolate my variable, and I get the negative x is greater than or equal to a negative 30. Now, this is not solved. I still need the coefficient of this term right here to be a positive 1. So I've got to divide both sides by a negative 1. And whenever I do that, again, if I multiply or divide by a negative, I've got to flip the sign. So here's my solution. Graphing this on a number line, I'm going to say got 0, 30 all the way over here, and I'm talking about all the values that are less than. X is everything that is less than 30. So it's all of the values over here. This is approaching negative infinity. This has a equal to sign, and we did remember to flip that, so we know it's pointing the right direction. And it includes, because there's an equal to, it includes that value. So here's my graph and my interval notation reading from left to right. I'm going to say I'm taking all the values from negative infinity to a positive 30, including that 30. Okay, one last problem here, and we'll be done with this section. This is a really thorough covering of this section, so hopefully this is helpful for you. And I moved my board around, so let me make sure that it's good here. All right, there we go. Last problem here, going to be more fractions. All right, so we have a 2/5 x minus a 1/4 is less than or equal to 3/10 x minus 4/5. Now, I don't like that these have fractions, right? So I don't like that. So I'm going to use the LCD to remove the fractions. So let's identify the LCD here. My LCD is the smallest number that all these go into. Well, 10 is the biggest denominator, but 4 and 5 don't go into 10. 5 does, but 4 doesn't. So I'm going to go to my next multiple of 10, which is 20. All of them go into that, so my LCD is 20. So what I need to do is make all of the bottoms 20, or I could think multiply the entire equation by 20 over 1. I will show you both of those real quick, just for a review of how to clear a fraction. So there are two different methods. The top one that I'm going to do is the build-up method. So I'm going to build each fraction up to have a denominator of 20. So if I multiply this fraction by 4, I have to do the same thing to top and bottom. This fraction by 5, same thing to top and bottom. This fraction by 2, same thing to top and bottom. And this fraction by 4, same thing to top and bottom. that leaves me then with a 20 on all the bottoms. So I can just cross that out, and I would have then remaining a 4 times 2, which is an 8x, 1 times 5, a negative 1 times 5, which is a negative 5, 2 times 3, which is 6, x, and a negative 4 times 4, which is a negative 16. So here is my equation after I build up the fractions and clear them. You could also multiply each of these by 20 over 1, each fraction, by the LCD over 1. So this is just another method. Point is, we're just trying to get to this point in the solution. 5 will go into 24 times, 4 will go into 25 times, 10 goes into 20 twice, okay, and 5 goes into 24 times. So you can now see this is why the denominators are gone. When I canceled this, this is just leaves behind a 1, and you can see that the tops are the same. 4 times 2 gives me this 8x, negative 1 times 5 gives me a negative 5, still less than or equal to. 2 times 3 gives me a 6x, and negative 4 times 4 gives me a negative 16. Okay, so those are the two different methods of getting rid of those fractions. So we're just going to work with this equation now that we've cleared the fractions. And I want to isolate my variable. I'm going to move my variable to the left because it makes it really easy for me to read. So I have 2x minus 5 is equal, or sorry, 2x minus 5 is less than or equal to a negative 16. Still trying to isolate my variable and by doing addition or subtraction. I'm going to add 5 to both sides to get the 5 away. 2x is less than or equal to a negative 11. Divide by 2, and we get that x is less than or equal to negative 11 halves, which can't be simplified, but this is the same thing as 5 1/2. Just 2 will go into 11 5 times, there's a half left over. We never use this though. We'll always just leave it like this. Okay, so this is my solution here. X is all the values that are less than negative 11 halves. So I've got my number line, got 0, and here would be my negative 11 halves. Well, it kind of looked like I was drawing like a very unhappy smiley face. Yeah. Okay, so here's my 11 halves. We're talking about all the values that are less than that. X is less than, okay, or equal to that. So since we're talking about equal to, then we've got a bracket. That means that I'm talking about all the values from negative infinity to negative 11 halves with a bracket. All right, that's the end of this video. Hopefully this was helpful. Lots and lots of examples, so you can review this. Let me know if you have any questions.